Hey guys, today we're doing Chapter 2, Section 7, which is on step functions. So a step function is also called the greatest integer function, that's the actual name. We also call it the rounding down function or the floor function. This is what it looks like. So it's got two brackets, and the little brackets are at the bottom, and there's not brackets at the top. So this is called the rounding down function. And for every x, f of x is the greatest integer less than or equal to x. So basically what you're doing is you're just rounding down whatever's inside of it. So if I round down negative 2.2, that's going to round down to negative 3. 29 over 10, that's 2.9. If I round that down to the nearest integer, that's 2. 110 over 10, that's 11. If I round that down, that's still 11. And then negative 31 over 7, if I round that down, that gives me negative 5. So if I want to graph this on a graph here, the reason this is called a step function is because it looks like some stairs when you graph it. So we'll say that this is my y-axis. This is my x-axis. Okay, if I want to graph this, the easiest thing for me to do is to make a table. And I'll just think about what happens as these get bigger. So 0, let's try like 0.1, 0.9, and then 1, 1.1, 1.9, and 2. So when I plug a 0 in here, I get out a 0. When I plug a 0.1 in and I round that down, I get 0. 0.9 rounded down is 0. And then at 1, I get 1. Here, again, I'm at 1, 1. And then once I put in a 2, I'm at 2 now. So what we can see is that I'm getting closer and closer and closer to 1. But once I hit 1, that's when I actually change over. So I'm just going to start plotting these points. So 0, 0, I've got a point. 0.1, 0, I've got a point. I'll just call this 1. Okay, 0.90, I've got a point. So basically this is getting all of that. But then once I get to 1, now I'm at 1. So this right here is going to be a hole because I'm doing some sort of jump here. And then that pattern is just going to follow throughout the entire thing. Okay, so this would be my greatest integer function. As you can see, to draw this graph, you need to lift your pencil. This means that the graph is discontinuous. The values of x at which you have to lift your pencil to continue the graph are called points of discontinuity. So basically, anytime you have to lift your pencil off the paper, that's called a point of discontinuity because it's making the graph discontinuous. Let's say I have rolls of pennies that come in sets of 50. How many rolls can be made from 244 pennies? And how many can be made from p pennies? Well, if they come in rolls of 50, they have 244 pennies. I want to figure out how many rolls that is. So essentially what I'm going to do is I'm going to divide that by 50. And then I'm going to round down because I can't complete a roll without 50. So 244 divided by 50, that's going to be 4 point something, right? So when I round that down, that's going to be 4 rolls. So this is a perfect application of the rounding down function. If I want to do the same thing with p pennies, I'm going to take p over 50 and round it down. Okay, we also have the least integer function or the rounding up function or the ceiling function. It's essentially the same thing. The only difference is now I'm rounding up. So the brackets are on top this time to show that I'm rounding up. So here this would be 5. Negative 3.8, if I round that up, that's negative 3. And negative 1/2, if I round that up, that's 0. So now I'm going to graph this. I'm going to do the same thing that I did last time. I'm going to start by making a little table. So I've got 0, 0.1, 0.9, 1, 1.1, 1.9, 2. Okay, when I plug this in, 0 rounded up is 0, 0.1 rounded up is 1, 0.9 rounded up is 1, 1 rounded up is 1, 1.1 rounded up is 2, 2, 2. Okay, so now when I graph these points, it's going to look just a little bit different than my last graph, but it's going to follow the same basic concept. So 0, 0 is going to be a point, and then I jump up to 1. So when I jump up here, I'm at about this point here. And then at 0.9 and 1, I'm here as well. So basically this is going to be my hole now because that's where I jumped up. And then this is just going to follow that same pattern. So I'll have a hole here, and then a hole here. Okay, so notice that it's the same type of thing, it's just that your holes are on a different side this time. So a bus can hold 44 students. How many buses are needed to transport 100 students? Well, if I have 100 students and I know each bus takes 44 students, I am going to do 100 divided by 44, but then I'm going to round up because I can't have students left over. I need buses for every single student. So when I round that up, that gives me 3. So I need 3 buses. So then for S students, that would be the same thing, S over 44 rounded up. And that's everything for section 7.